Hi folks, this is a lesson on solving first order equations using separation of variables. That's a technique that won't always work, but it'll work if your equation has the property that it's separable. And I'll show you what that means in a minute, but we're going to start here with what I call the most important differential equation in the world, which I've written in shouty all caps so you really believe me. I'll emphasize this through the course, but this is a single linear differential equation that is relevant to models and also relevant to the analysis of more complicated differential equations. And what I'm going to do is I'm going to pretend like the dx and the dt are kind of separate entities, and the way you try to solve via separation is get everything involving an x on one side and everything involving a t on the other side. So I'm going to divide through by x, that gives me dx over x on the left, and I'm going to multiply through by dt, that gives me r dt on the right. Treating these as separate entities, I'm going to then anti-differentiate, right? And if we're thinking of x as being a positive quantity, I can lose my absolute values in the antiderivative. So antiderivative of dx over x is natural log of x. Antiderivative of r dt is rt plus constant that I've called c1. We would like to solve for the unknown function x of t. So to get x alone, I have to exponentiate each side. So x is e to the rt plus c1. Now please follow this closely because this isn't fancy math, but sometimes people miss this step. I'm going to separate this into two multiplicative terms. I can write it as e to the rt and e to the c1. And since c1 is an arbitrary constant, e to the c1 is an arbitrary constant, I'm going to give it a new name. I'm going to call it c2. So my solution is c2 e to the rt. Okay, this is an exponential function. It describes growth if r is positive, decay if r is negative, and I'll emphasize this again. The solution to the most important differential equation in the world is a growing or decaying exponential. In general, this technique of separation of variables works if the equation is first order. So, if you saw an equation that was like d squared x dt squared equals rx, you cannot solve that by separation, right? And the reason is that the separation that we do is really a trick related to the kind of like the chain rule of differentiation, and it doesn't work directly this way when we're dealing with second derivatives. So you can never separate a second order equation or higher. It's got to be first order, and then the second thing, of course, is that the equation has to be separable, meaning it has to be able to be written in the form dx dt equals something involving only x times something involving only t. And as a counterexample, you can consider dx dt equals x plus t, right? You can't factor that into something only with x's and something only with t's, so it's not separable. Let's do another example. We'll take here y prime equals ty squared with the initial condition y of 0 equals a half. I'm going to rewrite the y prime as dy dt for convenience, still equal to ty squared, and then I'll separate. So on the left-hand side, I have dy over y squared. On the right-hand side, I have t dt. I'm going to anti-differentiate each side. So the antiderivative of y to the negative 2 is minus y to the negative 1. And on the right-hand side, I get 1 half t squared plus constant c1. To get y alone, I'm going to take the reciprocal of each side and multiply by negative 1. So y is this expression here, 1 over negative c1 minus 1 half t squared. For convenience, I'll multiply by 1 in the form of 2 over 2. That gives me 2 over negative 2c1 minus t squared. But since c1 is an arbitrary constant, negative 2c1 is another arbitrary constant. I'm just going to call it c2. So I'm choosing to write the final solution as 2 over c2 minus t squared, where c2 is an arbitrary constant. Do you have to do that? No. You could have just left it with this, but I like for my solution to look as neat and tidy as possible. But I'll go ahead now and plug in the initial condition. Y of 0 equals 1 half. When I plug in, that tells me 2 over c2 is 1 half, so c2 is 4. And plugging that in up here, I get the final answer, y equals 2 over 4 minus t squared. So that's going to be our last example for this lesson, but you would like to be able to recognize when an equation can be solved by separation of variables, and then you'd like to be able to actually carry out that solution. Thanks for listening.